4 amps into a 120 volt outlet sounds smart. Until the wire gets hot, the charger trips, or your battery starts to die faster. Today we're cutting through the noise about level 1 charging on a regular 120 volt outlet. You've probably heard turn up the amps to charge faster, but that advice hides real risks. Overloaded circuits, excess heating cords and connectors, and subtle battery wear over time. I'll show the math, the rules, and the real-world numbers so you can pick an amperage that's fast enough for you, but safe for your wiring and your battery. By the end, you can download a free PDF in the description to learn about level 1 charging and how to improve it. Level 1 charging is simple. Household voltage, about 120 volts in North America, and a cable that plugs into a normal outlet. But simple doesn't mean no rules. A typical 15 amps household circuit can provide 1800 watts at 120 volts. But because the National Electrical Code treats continuous loads differently, you shouldn't run that circuit at night at more than 80% for a long time. That's 12 amps or 1440 watts. In plain talk, if you want your EV plugged in overnight for hours, design it around 12 amps on a 15 amp circuit, not 15. This is an electrical code safety standard, not a suggestion. Numbers matter. At 120 volts, 8 amps equals to 960 watts, which adds around 3 to 4 miles of range per hour. 12 amps equals to 1440 watts, roughly adds 4 to 6 miles per hour. 15 amps is around 1800 watts, which is not recommended for the 15 amp circuit. Most level 1 EVSEs and manufacturer guidance fall into 8 to 12 amps window for daily use because that balance keeps wiring cooler while still topping up. Typical level 1 output specs list 1.3 to 1.9 kilowatt as the possible range, but the safe continuous number lines up with the 12 amp rules. Why does pushing amps causing problems? Because heat scales with the square of current. The physics is simple. Joule heating says heat energy goes up as squared times resistance. Bump current from 8 to 12 amps, that's a 50% increase in current, but result in 2.25 times the heat in the same wire. In short, a small jump in amps can create a big jump in heat. And heat is what cooks insulation, softens connectors, raises resistance, and creates failure points. That's why wire gauge, connectors, quality, and continuous load rules exist. Now the EV battery side. Many people assume lower voltage and small currents never hurt batteries. Wrong. Battery aging is driven by factors that include temperature, state of charge, and how fast you push current into the pack. Fast charging and repeated high currents raise battery temperatures and can speed up processes like SCI growth and lithium plating, both of which reduce long-term capacity. Even though level 1 is slow, consistently running higher currents on a nightly basis raises pack temperature slightly, and those small cumulative effects matter over thousands of cycles. Reviews and lab studies show a clear trade-off. Higher charging rates accelerate degradation. All else equal, charging at the lowest practical amperage that meets your needs will tend to be gentle on the battery pack. So here's the practical trade-off. Bump amperage to get a few more miles per hour, but risk higher heat in the outlet, cord, and the car inlet, and possibly nudge the battery toward faster aging. Keep amps low and stay safe, but accept slower overnight top-ups. 3 specification pain points that crop up when people push level 1 amperage too high are circuits overheating and noise and strips, connector and EVSE degradation from repeated high current use, slight but meaningful increase in battery wear over time if higher current cause elevated pack temperatures and more cycling stress. And those are all small risks for a single night, but multiplied over months and years, they add cost and reduce reliability. Let's walk through how to choose the right amperage with numbers and practical steps you can use tonight. Step 1. Know the circuit. Open the breaker box and find the breaker for the outlet you plan to use. If it is 15 amps, assume continuous safe draw is 12 amps. If it's 20 amp breaker on the 12 gauge wire, 80% of 20 amps is 16 amps continuous, but most portable EVSEs and typical NEMA 5 to 15 outlets aren't built for that. If the outlet is old and has multiple devices on it, lives in a shared apartment circuit, choose lower. The NEC 80% guideline exists because wires and breakers heat up over hours and respect it. Step 2. Pick the amperage target based on your needs. If your commute is short and you plug in nightly, with 8 amps or 960 watts, is safe and gentle. If you need a faster top-up and the circuit and outlet are known good, 12 amps or 1440 watts is the usual upper safe limit on a 15 branch circuit. Avoid trying to squeeze 15 amp continuous from a 15 amp breaker. That's asking for problems. And step 3, check cable and connector quality. Thin, cheap cords have higher resistance and will heat up sooner at the same current. Replace worn cords and never use power strips on or unapproved extension cords. If you must use an extension, use a heavy gauge cord rated for amperage. But don't treat that as a license to ignore the circuit constraints. The heat is generated in the thinnest link, and cheap cords are the usual weak points. Step 4. Monitor temperature and performance. If the outlet face plate or a plug feels warm after an hour, reduce the amperage. If breaker trip, that's a clear sign you're over the safe continuous limit and you need a professional electrician. Step 5. Consider battery and EVSE behavior. Some cars draw a fixed limit regardless of the EVSE setting due to their internal chargers. Others allow you to reduce amperage in the car setting or on the portable EVSE. Using the car's software to limit current to safe levels buys convenience and reduces risk. Concrete example here. A US commuter with a 40-mile round trip driving a mild range EV that uses 3 to 4 miles per kilowatt hour. If the driver charges at 8 amps level 1 overnight for 8 hours, that's 7.7 kilowatt hour, or roughly 25 to 30 miles of range, enough for many commutes. If they set 12 amps, they would get 11.5 kilowatt, maybe 35 to 45 miles. The extra 10 to 15 miles may not just justify the higher heat risk if the circuit or outlet is marginal. So think about real need, not theoretical speed. Here's the key takeaway you need to remember. Higher amps on level 1 are not a free win. Pushing from 8 to 12 amps is a 50% current bump that creates more than double the heating in the wiring because of Ri square. That heat ages connectors and wiring, increases contact resistance, and can lead to higher internal battery temperature during charging, all of which accelerate wear. The safe, practical sweet spot for most home level 1 charging is 8 to 12 amps depending on your wiring and needs, with 12 amps being the upper safe continuous limit on the standard 15 amp circuit. Follow that and you avoid trips, fires, and hidden long-term costs. To wrap this up cleanly, level 1 charging is convenient, cheap, and gentle. When used smartly, respect the 80% continuous load rule. Pick an amperage that matches your real range needs. Use good quality cords and outlets. And don't chase a few extra miles per hour at the cost of heat and better battery life. The science is simple. Heat is the enemy and amperage creates heat like nothing else. Be conservative. Use 8 to 12 amps depending on your circuit. And call an electrician if you want faster, safer level 2 charging. If you want more details on this, I've provided a free PDF on this topic. You can download it based on the link in the description. Thank you.